people who are online, my mic was off for a second. They didn't miss that much. Just basically, we're going to be learning about inference. And today, it's a special class because we're actually going to be making something real. CS109 has the wonderful honor of being the place where the Stanford eye test came from, where we think about probability under uncertainty about whether or not a person can see based on responses to guessing different letters at different sizes. And I always want to make this a class demo, and now it is. And really the probability question that you're going to have to think through is, you have a belief about how well somebody can see. That user then is presented with a letter. We're going to decide how to, the size of that letter in a future class, but the user sees a letter, and then they either get it correct or wrong. There's a version of this where like there's an E up, down, right, or left. You're like, what is that? Is that some weird W? No, that's supposed to be an E or facing up. And then the user is supposed to guess up, left, right, or down. And if they get it wrong, your job is to update your belief in how well you think that the user can see, given that they just got that particular letter size wrong. And of course, this is very interesting because then you could figure out how well somebody could see over the course of a longer test. We'll learn how to do exactly that today. We'll do something incredibly real, incredibly practical in CS109 this Monday. Where are we in CS109? We're learning about probabilistic models, and it's such a wonderful time to be studying. Today, we're going to continue our learning goal of just combining Bayes' theorem and random variables. In fact, this task of inference is really just that. What happens to random variables when you observe information about other random variables? A little bit of review before we jump in. I have this fun little story. Once upon a time, wait, was it last time? No, a few times ago when I was teaching 109, I was going to have a baby. And so my wife was really pregnant, and I really wanted to figure out what's the chance of this baby showing on the due date or not on the due date. And because I'm a total nerd, I made a graph. And so this graph is an interesting graph. This is the probability distribution of when a baby shows up, where 0 is their actual due date. You know, babies are given due dates. Most babies are not born on their due dates. In fact, the most common date to be born is like 4 days after your due date. Am I making sense? I'm imagining babies is not that common in your guys' lives, but you guys can imagine babies and due dates. This is making sense? Okay. So this is the full distribution gotten from empirical data for quite a lot of years. There's been many babies. And we feel like this is the natural distribution of when babies arrive relative to their due dates. But the interesting question to me was, how does this probability change when I observed that the current date is like here? Let's say the current date is here. How does this probability change? You know, like, if the current date is here, is it possible for the baby to have been born here? Oh, assuming that there's no baby so far. No, you kind of have this thing where, like, if the current date is here, you kind of know an updated belief of all of these should be 0. And if the current date is here, you kind of feel like these probabilities should change, but it's a little bit unclear how they will change. And Bayes' theorem does give us this answer. So I'm going to let you guys sit with this for a second, warm up, talk to the person next to you, and then I'll tell you the answer in just a moment. But let's say D is the day when the baby comes, and I want to know what's the probability of this random variable. That's the task we're continuing to learn about, given that you observed no child so far up to this date. I'm going to give you the hint that a lot of times we're going to be using Bayes' theorem. So we have a prior belief about the probability of the child being born at a particular date. And what's the probability of no child so far, given that the baby is actually born on a certain date? It's something you can think about. If you think about these two things, you're making good progress. You're just left with this awful normalization constant. And I want you to just take a moment with the person next to you and try and think about, wait, do I actually know how I could get this term? And can I figure out how I would get that term? Think about with the person next to you. And if you're feeling super advanced, you don't have to do this. What would you do about this denominator? Okay, go for it. Have a nice little conversation. Let's have. Okay. This is a warm-up, but I will note it's a pretty hard warm-up. And to give you an idea of how hard it is, the first time this problem was posed to me was a year before my baby was born, when a colleague had a baby that was about to be born, and they came to me with this problem. They're like, hey, Chris, it's past the due date, and I need to know the distribution of when the baby comes so I can think about like my midterm exam. And so you can imagine as a colleague in the CS department, someone who thinks about this stuff, and it's a little bit tricky to come up with. First of all, did anyone have any questions about where you would get this term from? Anything confused? This term is this is my prior belief before I had any information, and that's what we call this term. This is the prior. It's just a lookup. You know, if d was equal to 5, you would be just looking up what's the value of 5 in your prior. That's all that is. It's a lookup of your belief before you see evidence. Now this term is a little bit wild. And this definitely is more, you need to think about what it means, then there is an equation for you to find. Here's an easier one to think about. Let's say that the baby is really going to be born on day 5. Or sorry, let's say the baby was really going to be born on day -43. So put it in -43 for little d. What's the probability of no child so far at this point? So the baby was really born here. What's the chance that you haven't seen the child so far? 0. Okay, that was good. Now, what if I flip it over here? What if I say the baby's really going to be born here? What's the chance that I've seen no child so far at this point? Okay, very good. I thought that was actually really tricky, but this value will either be 1 or 0. You either, definitely haven't seen the child, or you definitely have seen the child, depending on whether or not you've passed the date that the child's born. Super hard to think about, but what good practice for going between the world of probability and the real world. So this is pretty great. We can take every prior belief and either multiply it by 0 or 1, and we're left with this awful, awful term on the bottom. No child so far, not conditioned on knowing when the baby is born. Oh, did anyone have a good way we could do this? So probably no child.
Isn't that one?
It's the probability of no child so far. Yeah, let me think about that for a second. Don't know when the baby's born. No, it's not 1 because if the baby's, this is weird. This is why this term is called normalization constant. It's very strange to think through. You're not conditioning on when the baby is actually born, so it's possible in this term is still accepting that it's possible that the baby could be born before. So, capital D could equal to -47 in this term. Weird one to think about. Is there another way we can get rid of it?
I was thinking that this was based on the fact that a certain number of days had already passed, but that the area under the curve should always be equal to 1.
That's a very cool insight. And it's deeper than you might feel at first blush. It must be the truth that the area of this probability mass function must equal to 1. You know how this term is called the normalization constant? It gets that name because a lot of people find that the best way to calculate it is to figure out what value makes all of this equal to 1. There's a different way of getting to that exact same answer, which is what I have to do now is I have to do a law of total probability over D. And this is going to be the law of total probability of the probability of no child so far. So far, given D equals D. If you law of total probability this, you'll end up with the exact same result of just treating it like a normalization constant. So if you multiplied all of these, you would get some distribution. And the normalization constant will be whatever number it needs to be such that if you summed up all of these terms, it would come to 1. And I think that is exactly the right way to think about it. And it's the way I was hoping you guys would think about at this point. You guys might have noticed there's a massive vertical bar up here. So I really cared about this. I was doing this for my wife and myself, so I wanted to get things right. Does anyone have a guess for why there's this massive vertical bar and why the distribution doesn't just keep going? It's not just a truncated version?
That's the final date. That's the last day of the proof that hospital needs.
Yeah, naturally humans can have babies after this point. So this is the due date, and then like after this point, babies can come.
Was it the day after which she would just have a C-section?
Yeah, or it's not a C-section. It turns out if a baby, in most countries, if a baby is really, really late, they'll give you a drug that induces delivery. And so they kind of make the baby come. So this is the date of induction. So that actually is just the sum of all the probabilities of that date or afterwards. We've got a little bit too deep into babies, but if there was one major takeaway here, it's really this one. That one way to think about this normalization term is it is the term that allows the whole probability mass function to come to 1, which is a cool new angle on that term. Yes?
You know that the probability mass function has to be equal to 1?
Yeah, if you think about it, any probability mass function, like your belief in D, at any point in time, if you loop over all values of D, if you sum those up, it should be equal to 1. Because D is going to take on some value. And so one way of thinking about it is there is some unknown term here, K. Like if you just call this K, you can say there's some unknown term K. But I know that probability of D given no child so far, if I summed over all values of T, it should come to 1. That would allow me to solve for what K is. I can then say, the sum over all of these terms should be equal to 1, and then you can solve for K. Yes?
So is it like integrating from the left-hand side up until the current date, or from the current date to the right?
This one's going to be integrating over all the possible days that are still left. So it really is integrating over no child so far over all the values, given the values of D.
That there's no child so far is the same as the probability that the child will be born after
Today.
So far, yes, that's right.
Okay.
Okay. Good. We'll come back to this in a non-baby version. But if there's one major takeaway, I want you to start thinking about new ways of dealing with the normalization concept. Okay. And a little bit more review. We talked about Bayes' theorem a long time ago. We talked about random variables take on values are events. And so we can think about, hey, what's the probability of this event that m, this discrete random variable, takes on the value 2, given that this other random variable takes on the value 3, and we could just use Bayes. It's just events. Now, more generally, you start to see things like what we had in the previous slide, where you have random variable takes on any value, given other random variable takes on any value. And you have to generally solve for whatever insertion to n and whatever insertion to m. This is a more general statement, but the reason that the Bayes' theorem works the same is because this really is an event. It's just an event with an unknown input so far. Shorthand will often be used when you get to these complicated statements because people don't like to write random variable m takes on non-random input variable little m. So you'll often see this shorthand when people write this up. And then on Friday, we took this up a notch. We started thinking not just about discrete random variables, but continuous random variables. And we had this nice result, which is Bayes' theorem works whether or not you have a discrete random variable m or you have a continuous random variable x. So if they're both discrete, you just get exactly the Bayes' theorem you thought. But if one of them's continuous, you get Bayes' theorem. It just happens that when you're talking about the continuous random variable, instead of using the probability mass function, you use the probability density function. So the probability density function is like your expression of likelihood for a continuous random variable, and probability mass function is the expression of likelihood for a discrete random variable. Intuitively, this feels very good, and then we mathematically showed why it's true. And it just doesn't matter what combination of continuous and randoms you have, as long as the thing on the left-hand side of the bar is continuous, use density. And if the thing on the left-hand side of the bar is discrete, then you use probability mass. So Bayes, it works in all the ways you'd want. Just if something's continuous, use probability density. Okay, and that works true for the law of total probability. So if you want to know the density at x, you could use the law of total probability over some discrete random variable n. Again, you just use density when you have a continuous random variable, and use probability mass when you have a discrete random variable. Okay, and then in class we worked on this problem. We thought, what's the probability of the gender of an elephant given the weight of the elephant. We've told that gender equals 1 has this weight distribution, and gender equals 0 has this weight distribution. And we want to just infer the probability distribution over G given an observation to X. And I want to lightly point out that I've told you before, if you have multiple random variables, the thing you would need to solve anything is this thing called a joint. And the joint says what's the likelihood of particular combinations to random variables. So like G equals 1 and X equals 72.3. You've given me an assignment to all the random variables, and you should be able to talk about the probability of those two things together. And we do have that in the problem because we could decompose this, like the probability of the gender and then the probability of the weight given the gender. And so because the problem has given us the probability of the gender, check, and the probability of a weight given the gender, then we could figure out exactly the joint probability. I just want to note that it's implicitly there. And you could do this more generally. But if you wanted to solve this problem, what we did in last class is we set up a Bayes theorem. We said we want to know probability of G equals 1 given a particular weight. And so we had probability G equals 1 given X equals 163. And that was equal to the density of X equals 163 given G equals 1, probability that G equals 1. And then here we could use a law of total probability for the classic version of Bayes that we love. 163 given G equals 1 times probability G equals 1 plus the density of X equals 163 given G equals 0 times probability G equals 0. So it's just Bayes' theorem. It's just our events are assignments to random variables. And in this case where we have a continuous random variable on the left, we use the PDF. What's the PDF here? Oh, that's a little scary. Why is it a little scary? Because you're like, what is that? Well, X is a normal. If G equals 1, then we know that X is this normal. And you know what normals have? Oh, sad times. What do normals have? A probability density function. They have a cumulative density function and a probability density function, and what you're going to put in right there is that normal PDF. Whew, what a time to be alive. I'm going to get more into this Wednesday, but I'm going to start showing you that when you have big models of lots of random variables, there is this way of visually drawing them, and because they gave you gender and then they gave you weight given gender, this picture is actually implicitly behind the scenes, that we imagine that the gender is what's causing weight, and so that you can give the joint by first giving the gender and then the weight given the gender. That's not that important right now, but it will be more important on Wednesday. Okay. Wow, what a lot. I do want to give us one more piece of practice. On Friday's class, we did this project where we thought about the situation of trying to decide if a baby can hear or not. So play a sound, and then the baby will look up or not based on whether or not they hear the sound. But we have this problem that sometimes babies look up when they don't hear the sound, and sometimes babies won't look up when they do hear the sound. There's some stochasticity, even though there's a probability distribution. So if we want to infer whether or not a baby can hear, given their response to sound, we need to use probability. But now I'm going to bump this up a notch. So for babies who can hear sound, when a sound is played, their gaze moves by a continuous random variable. So if you play a sound, there's a good chance that their gaze moves by 15 units. And there's some variance to it. It's possible that their gaze moves by 0 units. It's possible that it could be negative. If a baby can't hear sounds, there's still a distribution for how much they move their head. It's just a different distribution. So if a baby moves their head 14 degrees after you play a sound, you can't conclude with certainty whether or not the baby can hear, but you can update your probability. So my question for you guys, a little bit of practice is, under this normal assumption where we're given distributions of how much babies move when a sound is played, can you update your belief? So again, take a little time for practice. I'm actually going to give you guys a minute and a half to think about this because I think it's very important. In fact, some of the hardest problems on the midterm often take this form. So if you feel uncomfortable with it, great, you have something to study. And if you don't feel uncomfortable with it, wonderful, you're in a very, very good place in CS109. So let's see if we can think this through. How could you figure it out? Okay, I'll erase the board while we think about it. Inference is hard. But if we want to be able to do that Stanford acuity test, we need to get very comfortable with inference, because right now I'm going to tell you what we're doing here is we're updating the belief of a Bernoulli given the observation of a continuous. And we want to do the Stanford eye test. We're going to have to be able to update a belief about something much more complicated than a Bernoulli. So we really want to feel comfortable in this space before we can do something more complicated. I know this is hard. Okay, but at the same time, it's not that impossible. You just have to follow the recipe. The recipe often involves your first step is to write your random variables. Like if you get to a midterm problem, you don't know what to do, write random variables. You'll probably get some extra or like partial credit even if you don't get the answer past this point, but defining your random variables really matters. And once you define your random variables, then write what the question is asking in terms of those random variables. And in fact, then you've really set yourself up for success. So if I say H is a 1 if the baby can hear, I'm going to say it's a Bernoulli random variable. You could have had an event without a random variable here, but I'm going to get in the practice of using random variables in place of events. And if it's just binary, I'll use a Bernoulli. So what's the probability that H equals 1 given that X equals, what was X? 14? That's what we want you to calculate. And the only reason this is a little bit difficult is because the thing you're conditioning on is continuous. So you have this continuous belief over how much the baby's view will change. And because that's continuous, we're going to have to use that other version of Bayes where we don't use the probability mass function, but use probability density function. So I hope when you guys got to this point, a natural thing to do was f of x equals 14 given h equals 1 times the probability that h equals 1 divided by, and you can call this a normalization constant or you can expand it out. You can expand it out by thinking about the case where h equals 0 and h equals 1. There's several ways you could deal with this. The probability that h equals 1, that's your prior belief. I think I forgot to mention here, but we're going to assume a 1/2 prior. This is a pretty safe assumption if you don't have a belief otherwise. But then we still need to put in this term. And for this term, I've told you that the child is hearing. So when the condition gets flipped, you're told what is the state of this unobserved hearing variable. You're told that hearing is in fact 1, and then it's how likely is x to be 14 if hearing is 1. Can somebody help me out here? What is this? And actually, if you had to write this in Python, it would be like scipy.norm.pdf. And what are the values of norm's PDF? You have to say, what is the value it's taking on? You have to say, what is the mean of the distribution? What's the mean of this distribution?
50.
Yeah. Because we know h equals 1, we know we're talking about this normal, not that normal. And then you have to put in the other parameter, which is annoyingly in scipy, the square root of the variance. Now, you could have written that, or instead of writing that, you could have written what this actual mathematical equation is. If you want to write what that actual mathematical equation is, we have it right here. It's 1 over sigma square root. Sigma is the square root of 50, and then you have the square root of 2 pi e to the power of negative 14 is x minus the mean divided by the standard deviation, which is the square root of 50 squared. Did I miss anything there? Oh, the minus 1/2. And you can put that term in and you multiply it by 1/2. A nice thing is if you followed through with this problem, all of these terms would end up canceling out and you just get this nice little expression on the top and you get similar expressions on the bottom. We haven't dealt with the bottom term, but as I said, you could just expand it out by thinking about the case where h equals 1 and the case where h equals 0, like our classic Bayes theorem. But I know this is hard, so what I want you guys to do is I want you guys to tell me what's confusing about this. Like, what's hard about this? What could I go deeper into?
So how would you do this on the term?
Good question. The good question is, how would I do this on a midterm? Like, I can't calculate this by hand. You don't need to calculate this by hand. So there's two valid ways you could answer this problem in the midterm. This is an answer on the midterm. Like, that would be like the answer, assuming you fill in the denominator, that's the answer we would be looking for, and you don't have to solve it. The other thing is, if there's a time where you want to use a Python function, we'll let you use a Python function. We just kind of assume you would be able to use a computer if we gave you one. So if you say like, calculate this using SciPy, I'm fine with that too. Okay, yes?
Like you're using all PMFs. In this case, we're using PDFs. But PDFs don't return probabilities, right?
That's right. They give you back probability densities. And it's amazing that if you multiply this probability density by this probability and then divide by this probability density, you're still left with a probability. And that does come from the fact that there is this epsilon trick we use in the derivation. And that epsilon trick is allowing this probability density to convert to a probability and back. So if you check out the derivation, there's a nice reason for why, but you're absolutely right. It's just not a problem, which is a beautiful thing. And it's a mind-blowing, beautiful, wonderful thing that you should use in your life and on the midterm question. Yes?
Could you explain again why P h equals 1 is 1/2?
Oh, this is your prior belief in whether or not the child can hear before you see any evidence. So it's like you haven't even met the child. What's your belief that they can hear? And sometimes you have reason for a deeper belief in what your prior is, and sometimes you don't. And if you don't have a deeper belief, then like the uniform prior is pretty reasonable. So the probability that h equals 1 equals the probability h equals 0 seems very reasonable to me. The problem should give that. Otherwise, it's the problem writer's fault. Yes?
How does CDF fit into Waze?
So the CDF isn't really helping us here. The CDF was such a beautiful thing if we wanted to answer probability questions about a normal, like what's the probability that a normal takes on a value in a particular range. But the CDF doesn't even come in here. I suppose if I told you like what's the probability of hearing given that the child heard, moved less than 14 degrees, then that would allow you to use like the CDF on this side. But yeah, a lot of times with Bayes' theorem, the PDF is more useful. So the PDF, you needed to know it for this reason. Okay, you guys are wonderful. I know this is hard. But those two problems, if you can go practice them, I think you'll really appreciate that come Tuesday. Again, I just want to gently note that there is this implied way of expressing the joint distribution here. We're saying that we think it's the hearing that causes the gaze change. And so first you want to know the hearing, and once you know the hearing, then knowing the gaze change is a little bit more straightforward. And there's kind of this implied causality, and we're going to get way deeper into that in Wednesday's class. But they give you the joint by telling you the probability of hearing and then the probability of gaze change given hearing. As I said, if you want to solve all probability questions, you want the problem asker to have given you the full joint distribution. Okay, are you guys ready? We are going to bump this up a notch. These have been hard problems, but there's one thing that's made them easier than what we're about to do. The thing that makes it easier than what we're about to do is a lot of times what was on this left-hand side was just a Bernoulli. It's like you had one belief value and it was updating. And now I want us to think about what happens when your belief distribution's not a Bernoulli. And we're going to be doing this by coming up with a better eye test. So in CS109, we started using probability to think about estimating how well somebody could see. So you can go to myeyes.ai and you can run this CS109 algorithm. And if you go to run that CS109 algorithm, as you answer questions, you can watch the belief distribution, how well you can see change. This is the old problem what we're solving. Has anyone ever taken one of these eye tests? Yes. Oh, brutal, right? They like ask you this row and then they ask you this row and then they ask you this row. And there's two big issues here. Like, it doesn't allow for you to ask questions that are between these font sizes. And then a lot of times there's stochasticity and randomness that's not being taken into account when they score you based on this exam. Like, maybe you kind of see the number and you're guessing. Maybe you make a mistake and you kind of knew the letter, but you said it wrong anyways. And without thinking about all this probability, they actually end up in the wrong answer a lot of the time. So this is an explanation of like what 109 is able to do. This is your normal eye exam. 20 is the normal amount of letters that you have to answer. And on the y-axis is how wrong it is. You want to be low on the y-axis, and this is pretty high. This is relative error is just like the percentage difference between what the exam says you can see and how well you can actually see. So you can see there's kind of some error. It's not 100%, but it's notable. And longer tests don't really help that much. If you wanted to do a clinical trial, you use the much bigger version of the exact same test, but it still has pretty high error. There is this really cool dude in Switzerland who came up with this algorithm that we learned about later. And that algorithm didn't use a lot of probability theory, but it did some nice adaptive answering. But then we came up in CS109 with the one that used the nice probability theorem. And you see we could get like way, way, way reduced error rates. And it all just comes from a little bit of thinking about probability. And you'll be surprised how simple it is. Like you're like, hey, it's just Bayes' theorem with a nice little normalization. Mind blown. And like, from 1800 until 2000, I think it was 2 years ago, people just didn't think about applying Bayes' theorem in this way. Okay, so let's tell you this story, and I'm going to give you a way of representing how well somebody can see. We're going to represent how well somebody can see as a random variable, and we're going to consistently use the random variable name A to represent how well somebody can see. A, can you think of it as ability, or if you're really fancy, you can think about it as acuity. Acuity is the really technical term for ability to see, or that's visual acuity. So this is a random variable. It's a random variable, and therefore you want to give the whole distribution. If that random variable is continuous, you should be giving a probability density. If that random variable is discrete, you should be giving some function that, a probability mass, which represents whether or not, or the different assignments of little a to their probabilities. This is the cheekiest thing that we did. Ability to see really should be continuous. So if 0 is like you can't see at all, and 1 is standard vision, ability to see in the natural world is continuous. But to solve this problem, we did something that you guys probably desire to do many times when you see continuous random variables. We discretized it. We said, sure, it's continuous, but what if we represent it as like 200 points? So we can say like, or let's say 100 points. So you have ability to see as 0, ability to see as 0.01, ability to see as 0.02. We took something that's truly continuous and made it discrete by making 100 little bins. And we thought about, if your true ability to see is 0.2222222, we'll just truncate that to 0.02. Wild. Does that make sense? Okay, then as soon as I tell you that, now you have a discrete distribution. And what I'm showing you is your prior belief in the ability of someone to see. So this comes from historical data. We've got lots of data from around the world of people's ability to see. And here's what that prior belief looks like. What is this prior belief saying? Is it saying that more people can't see or that more people can see? Like when someone walks into this exam, are you more likely to believe that somebody can or cannot see? I'm just going to give you guys a second to think about this because it's important. We're going to build on this chart a lot in the lecture. Low probability here, high probability here. We think that most people walking into this test can see. You can change your priors. Priors are philosophical. Different people could say, well, I think my particular clinic has a prior that looks like this. Or you can say, I don't want to make any assumptions, so originally I'm going to assume everything's equally likely. All valid priors. But what we're going to be using first is the historical prior. So like this is the prior of abilities of people to see. Yes?
When doing that, would you choose the value with the top probability, or would you choose the expected value?
Such a good question. I'm so glad you asked that. Okay, so when you talk about how well somebody could see, a lot of us think of a number. But from today on in CS109, I want you to think about the whole random variable. If somebody says, what's your belief that somebody can see? It's not a number, it's a whole distribution. And that distribution relates all possible numbers to their corresponding probabilities. If you force me to choose a number, I could choose expectation or I could choose mode. But never force me to choose a number. I would much rather have a random variable than a number because a random variable keeps track of all the possibilities that it could take on. And it keeps track my own uncertainty that maybe somebody really could see not very well. And so I love random variables, and I think if you reduce it to a number, you've just lost so much. And there's a little tear in my eye when somebody makes me do that, but that's not important right now. Okay, other questions about this? Okay. Now, in your computer, we haven't talked too much about how this gets represented in computers, but if I'm representing this probability belief in a computer, And if I've discretized it, there's a pretty reasonable way that I could represent this. I could represent it as a dictionary. So a dictionary has keys and value pairs. And so I'm going to have a dictionary where if you put 0.09 in for the key, I'm going to give you back the prior belief. This one's calculated for you from historical data, but this is how we're going to be representing our random variable. Does that make sense? Like on some level it might be intuitive, but again, there might be something confusing. Is there anything confusing about this? You could have written this yourself if I gave you the data, but that's not what we're going to focus on today. Okay. You guys following along so far? Please ask me questions because I will just keep building. So again, your prior belief, you can represent it as a graph, you can represent it as a dictionary, but these are just two different representations for the same thing. They're both representing the random variable, and they're both representing, for any assignment, what is the corresponding probability. Okay, this is not that important, but if there's a doctor in the room, I know you guys do logarithmic units, and I've simplified this a little bit for class. So just before you use this in a real medical case, just come talk to me. Okay, now, you had that prior belief. So before the patient walked in, you had a belief about how well they can see. Let's say, to start off, you show them this font size. So there's a particular font size 0.7, and they get it wrong. Getting it wrong, we're going to represent as there's a random variable y. Y equals 1 means they got it right. Y equals 0 means they got it wrong. You observe that they got it wrong. What happens to your belief? And as soon as you hear those words, I want you guys to start dreaming of Bayes' theorem. You're like, I have a random variable, I observe something, and I want to change my belief in the random variable. That's exactly where this wonderful equation is most useful. I will let you know that if we did Bayes' theorem correctly, you'll watch your distribution change. They just saw a really large letter and they got it wrong. So now it starts to become really believable that they can't see that well. Whereas in our prior, we thought most people could see pretty well. Now that they got a big letter wrong, we're like, uh-oh. We're not going to rule out the chance that maybe you could see pretty well and you just got unlucky. But now we start to believe, okay, maybe we're talking to somebody who doesn't see that well, like me. So if I could put this together all in one chart, it looks like this. You have a prior belief. Then you see an observation. That's a particular font size. They got it wrong. And then you want to update your belief. Well, ours had something that was a little flatter because I put in two different numbers when making these slides. But your updated belief looks like this. And the way we're going to get there is through Bayes. And Bayes says, this thing I care about, the belief and ability to see given your observation, is hard to think about, but the flip is much easier. The probability of seeing this observation given I tell you how well somebody can see, you have to have a prior belief and you have to deal with the normalization constant. But we're going to use that idea from beginning of the warm-up that this is just going to be whatever number we need it to be such that for all values of a, this thing sums to 1. It will truly be a normalization. So hopefully you guys see that this is a cool thing to have. Like, how nice would that be? So that's what I want you to see about this equation. And I want you to see about this term that this is something we already have access to. Somebody has told you their prior belief. If you had a particular value of 0.5, for example, you would just be looking up in your dictionary what is the probability associated with 0.5. So if this is the probability a equals 0.5 giving y equals 0, you would just look up probably a equals 0.5. I'm leaving a little variable here because I don't just want the belief of ability taking on one number. I want the whole belief over all possible numbers. I want a whole freaking probability mass function. Okay, which must leave you with a question, which is just like, how are we going to get this, the likelihood term? How likely is your observation given I tell you the value of the thing you're trying to infer, the hidden variable? We often think about this thing as the hidden variable, the unobserved. You can't open up someone's eye and see how well they can see. Instead, you infer it based on evidence. I'm going to leave this here because if there's one most important slide of today, this will be it. So we should think about it for just a second. Man, how many times do you see Bayes' theorem in this class? How many times do you see Bayes' theorem in the world? There's a beautiful book called The Theory That Will Not Die, and it's just all about Bayes' theorem and how it just shows up every single place in the whole world. Bayes' theorem, what a thing. Okay, are you guys following along so far? are you left with this mystery of where does this equation come from? Think about it semantically. I will tell you exactly how well the person can see, and then I want you to tell me how likely it is that they got it wrong. A couple key takeaways before I talk about this. That cell phone tracking problem that you guys had to do on your problem set was really warming you up for this world of random variables. Because if you think about it, that cell phone location could have been one random variable where it takes on values of all those locations. We thought about it as like 16 different events, but you could really think about it as one random variable with 16 assignments. And those two things are going to map very nicely onto each other. Some beliefs can be represented, like if you have a random variable, you really want a function, which is like the probability mass function or the probability density function. Sometimes it's hard to represent beliefs as an equation, and if you're a computer scientist, a dictionary is a pretty cool idea for representing a random variable. I just wanted to mention that. Okay. And then I also want to mention this cool little trick I did, which is I took a continuous random variable and I discretized it to make my life easier. Okay, and then once again, there is an implied causality in the world. We are saying that it's ability to see that causes you to get a problem correct or not correct. The converse would be pretty ridiculous, like whether or not you get it correct is the thing that tells you whether or not a human can see. I mean, knowing this allows you to estimate ability, but in the real world, it's ability that's causing correctness. And again, we'll get more into that on Wednesday. So now let's take a moment and talk about this equation. I'm going to tell you the real deal, but I'm not going to test you on it. Like on the midterm, I'm not going to ask you about the education theory that explains this, but I want you to understand where these could come from. Are you guys ready for it? There is a world in education that talks about exactly this, and let's write about what we're curious about. We want to know the probability that y equals 0 given ability equals a. Oh, sorry, probability. So y equals 0 given ability equals a. We're going to want to be able to do this for any value of little a, but let's put in a concrete number so that we can think about it. So if I tell you someone's ability to see is 0.a, what's the probability that they get it wrong? Does that make sense to people? As what we're asking? Okay. So it comes back to this thing called item response theory. Item response theory is an old theory that people have had since the 1950s, which says if you take a person and you match them up with a question, maybe it's a question on an exam or maybe it's a question on an eye test, we can talk about the probability that that particular person gets it right. And since the 1950s, people have been making this assumption. Every person has an ability and every problem has a difficulty. This is really the model people use. They take the ability of the person, subtract off the difficulty of the task, and that will give you a number. It's not necessarily a probability. And so they take that number and put it through a squashing function that gives you a probability. And if I had to plot this particular squashing function, this sigmoid is a squashing function, which is if you put in a really large number, it gives you something close to 1. And if you put in a really negative number, it gives you something close to a 0. In fact, if you put in a 0, it gives you a 0.5. That's the sigmoid. And the sigmoid function is basically a really cool hack to take any number and make it look like a probability. And that's what people use. Have you guys, the adaptive GRE uses this. When people normalize on the GRE, they're using this. If you take the, any of the big tests like the TOEFL, this is the theory that people have behind the scenes for probability that somebody gets things right. The reason they have this theory is because they want to figure out how difficult their problems are and to figure out how strong their students are. So this is a probability. It says, if you tell me the difficulty and you tell me the ability, you just put this through a function and it gives you a probability back. So the probability that y equals 0 given a equals 0.8 is just going to be plugging into this equation. You put 0.8 for the ability and then you put in the difficulty. And you're like, wait, what's the difficulty? Well, if you know the size of the letter, the difficulty is just going to be a function of the size of the letter. So big letters are going to be thought of as easy and small little letters are going to be thought of as difficult. You can just imagine this is equal to 1 minus the font size. So if I tell you 0.8, and I know the font size, I can take 0.8, subtract off my function of the font size, put it through the squashing function, and I get a probability. I'm just going to go a little bit deeper if you guys bear with me for a second. Okay, any questions about this? As I said, item response theory, not on the exam.
That we did like a while ago, or the question about multiple choice questions, like taking that a step forward.
Yeah, absolutely. Yes. And actually, that does lead to this one other thing. So item response theory says the probability that person gets question J correct is this nice little formula, where sigmoid is not it's not the standard deviation of anything, it's this particular function. There's a little bit more to it if you're curious. We think about guessing. We add in the probability that maybe somebody just guessed and got this correct. And we think about slipping too. Slipping is when you know the answer, but you just get it wrong anyways. And so we just think about cases. We think about the probability of or. It's like either you got it right because you guessed it right, or you got it right because you actually knew the answer. So we think about this as the probability that people actually know the answer. And then slipping, like maybe you know the answer, but then you just like accidentally fill in the wrong thing just because there's a 1 in 100 chance that you just make a mistake. All of this would allow us to just have a function where if you give me ability, I can straight up calculate the probability that you get it right. Sorry, all this gives you the probability that you get it right. And if somebody tells you the probability you get it right, and you want to know the probability that they got it wrong, it's just going to be 1 minus that. Which kind of brings us back to, if we go all the way back here, what I'm telling you is that we just have a simple function. If you give me ability and you know the font size, you just put those two things into a Python function, and it'll give you the probability that they got it right back, and then you can do 1 minus that to get the probability they got it wrong. Cool aside? Okay, I tried teaching this class once before and I didn't give people that aside. I really didn't want to lose people on it, but I thought actually you'd get more insight just knowing a little bit deeper what goes behind the hood. You could just think of it as the problem statement gives you this term. Or you could know that item response theory is the secret sauce. Yes?
For the graph that is on the slides, does it go up again for 1 exactly because it thinks somebody has slipped?
Exactly. So here there's some probability that they're strong in the graph I showed you. And it's because it thinks that there's a chance that somebody came in and was strong and then got the question wrong only because they slipped. Like they knew the answer and they just happened to just blurt out the wrong answer. So there's still some belief that they're strong visually and they just got unlucky. That's exactly why. And it turns out we did this thing where we tested out all of our different modeling decisions and which ones mattered the most. And it turns out putting in guessing and slipping were critical to be able to really come up with the right answer after somebody answers 20 questions. So there you go. Okay. So we're going to practice thinking about Bayes' theorem, but then I also want to point out what happens if you have multiple observations. So we talked about observation 1. So in observation 1, you have a belief. You see them get some letter wrong. Let's say it's at font size 0.7. And then you update your belief using Bayes' theorem. What if then you see another letter, like we give them a larger letter and they get it correct? How do we deal with multiple observations? Because we think of each observation as being independent given ability, it turns out this becomes just this posterior, like after you calculate this, wait for it, in your second observation, it becomes your prior. So it's like in your first observation, this was your prior, but then you saw something, this became your belief. And then your second observation, that's now your belief, and you get a new piece of evidence, and then you change your belief. If you had a third observation, this would then become your prior. Yes?
Because you're using like the previous step as the prior for your next step, does it mean that the order of the questions might influence what the final probability looks like?
Because of the independence that's actually true, it turns out order won't matter. So good question, very good question. Okay. This is what, okay, posterior becomes our new prior. But really, this is what I want us to be able to program. Whether or not somebody gets something right or wrong, for a particular font size, I want us to be able to update our belief. Did you guys get our goal? And then doing multiple will be very straightforward if we can just program this Bayes' theorem. Shall we? I think we should. Okay, to the code. So what do I have for us to start out? Oh, that's our website. That's also our website. To the code. Here's what I have for us. So first of all, I've got a function called getPriorProbability. And if you call getPriorProbability, it will give you back a function. I also give you a function called plot, which will take this dictionary and plot it. So if I run the starter code, it just plots. This is your belief somebody walks into the exam, and without seeing anything about their eye, this is your belief that they can see. Sound good? We're then going to observe something. We're going to update our belief given the prior, and then also given an observation. An observation has two parts. Hey, people in the back, can you guys see this? You want font bigger? Just yell it.
My vision's bad.
Mine too. I really appreciate that. This is going to be the test for us. In fact, it turns out this test is really important for people with bad vision, like myself. Okay. Good? Okay. So a belief has two parts. Or sorry, an observation has two parts. When somebody answers a question, you see two things. You know the font size of the question that was asked, and then you see whether or not they got it correct, and the correct is going to be a Boolean. So we're going to want to write a function called update a belief that can take in an observation, so any font size and whether or not they got it correct. You know, here's a different observation. In this observation, they saw a bigger letter and they got it correct, whereas this one they saw a slightly smaller letter and they got it wrong. The letters go from 0 to 1, so these are both big letters. Okay. Now, update belief is really what we need to write. What I have here creates a posterior, but if you read it carefully, it loops over every value in ability, so every possible assignment to little a, and it just looks up the prior, and it says the posterior is equal to the prior. It doesn't do any updating at all. And then it returns the posterior as if it had done some work. So cheeky, it's done nothing. It's just basically copied over the dictionary. And so if you call, you can have all these changes you want. Oh, Python 3.9. I haven't installed tkinter on my Python 3.10. We saw all these observations and we haven't changed our belief at all. So bad. We must be more flexible. We must change our belief when we see evidence. We all must do this. Yes, question?
Just a question about the graphs. Are they specific to each size of the letter?
No, the graph is just your plot of ability to see. And so they're not specific to the size of the letter at all. If we go back here, I can look at one of these graphs, and I don't need to know the history of the test that they took, and I can just see that this says, you think the person can see pretty badly, because this is poor vision and this is good vision. And it doesn't matter what the font sizes were of the question. This is just an expression of how well a person can see.
So the letters can come in different font sizes, right?
Yes.
So does the size of the current letter affect the size?
If you got to the solution, and when we get the solution right, if you put in different font sizes, it's going to have a really big impact on your belief. So if you get a small letter wrong, that will change your belief in a really different way than if you get a big letter wrong. But at the end of the day, we're going to be plotting these beliefs of ability to see. So it's like what happens in this middle step is affected by the font size, and it will certainly tell you how the prior changes the posterior. Okay? There's one other thing that I've got for us. I wrote item response theory for you here. I said, if you give me the font size, your difficulty is equal to 1 minus the font size. Why did I do 1 minus? Well, because large letters have large font sizes, but they're easy. And small letters have small font sizes, but they're hard. And so the 1 minus allows us to say, okay, go from font size to difficulty. And then the sigmoid function of ability minus difficulty, that was item response theory. And I totally recommend you guys think about why I got slip times guess plus 1 minus slip times the probability that came out of item response theory. That's a super interesting thing to think about if you guys want to just push yourselves a little bit. As I said, it's not the point of this class, but I think that's fascinating. Then also the scaling factor, it's like a super extra feature of item response theory, which we don't need to get into. But I do give you the probability of correct given ability. But it turns out the probability of a correct given ability is super misleading because your observation might not be correct. If your observation has somebody who got it correct, you should be giving back that number. But if the person got it wrong, you need to be giving back 1 minus the chance that they got it correct. So going back to the slides, Item response theory gives you the probability that y equals 1 given a equals little a. If you want the probability that y equals 0, you have to do 1 minus that value. Everything in the world's a potato or not a potato law of probability. Okay, so all this means that when you package those together, I give you the probability of an observation given ability. So probability of observation given ability is basically writing this, probability of an observation given an ability. So this whole expression just becomes a function call that I give to you. And come talk to me about item response theory, you can go deeper into it. So now we have probability of observation given ability, and our job is to write this function. You saw an observation, and you're not going to change one ability, you're going to change your belief in the entire ability. So we're going to calculate a posterior, we're going to loop over every value little a, and for every value little a, we can look up its prior, and we can do one more thing. We can now call this function. We can say, what's the probability with a particular ability of seeing this observation? So, we're passing in this observation, and we have a function which says what's the probability of observation given ability. I really want you guys to think about what this for loop is doing. This for loop is going over your entire assignments of little a. So before you had this belief, right? This for loop is saying, okay, what if a equals 0.0? You can look up the prior, and you can say, how likely is the observation given this value of little a? And then we do 0.01, and we go through the next iteration of the for loop. You look up the prior belief of that, it's just this value, and then you can figure out what's the probability of this observation given a equals 0.01. And the for loop, we're going to try every single value there. So if we call this probability of observation, in the Bayes theorem, we have the prior belief. I'm going to call this prior belief. And these are actually, I like the little I because, actually, I'm going to call them little a's because I feel like that's a little bit nicer for you guys. So we're going to loop over all the assignments to little a. And then now we need to say, what is our posterior belief of somebody's ability to see being equal to that little a? I want you guys to think about what goes in here, because there's only 2 lines that you would really need to make this whole probabilistic thing work. But you need to get those 2 lines perfect. And so you need to go deep into your theory. So in this posterior, where is this coming from? Think about it with the person next to you. I'll start writing on the board, and then we can code it up. Okay. Okay. If we were going back to our world of hearing or elephant weights, you don't need a for loop because the values of the random variable you're thinking about can only take on the values 0 or 1. You only need to calculate one of those, so we could do Bayes' theorem without a for loop. But now we're inferring our belief about a random variable called a. And a can take on 100 values, 0, 0.01, 0.02. And so if you want to infer a, you can't just use Bayes' theorem once. Instead, we're going to have a for loop, and we're going to think about, for every assignment to a, what is our updated belief? That's what this for loop is. So we're not just going to do Bayes' theorem once. We're going to do Bayes' theorem thinking about a taking on the value 0.0, 0.01, 0.02, 0.03. So this overall for loop is going to loop over all the values of little a. So when I say ability a, that means, little a. We have, this whole thing is going to calculate the belief of capital A, and we're going to for loop over all possible values little a. For every possible value little a, we have the prior. You can look up the graph before. That was your belief before you saw this observation, because don't forget, we're updating our belief in capital A for an observation. We know if you tell me the value of little a, we can say how likely is the observation. Like we're given this term, the likelihood of the observation given a equals little a. And then Bayes' theorem says you just multiply these two together. You take your prior and multiply it by the probability of observation given your prior. And then you solve for this. I'm going to do the cheekiest thing. I'm going to pretend that this doesn't even exist. I'm just going to be like, I don't even see you. Huh? Like what normalization constant? And I'm just going to do this numerator term. And then we'll get to the wrong answer, but a helpful wrong answer. So I'm going to run this Python. This is our starter code. Starter code. And this looks exactly right. It's not right. If you were very careful and you calculated the sum of all these probabilities, they won't sum to 1. And if this is a proper belief, then either the area under this curve, however you like to think about area under this curve, should be 1. And basically, this looks right, but if you were very careful, the y-axis is wrong. And it's because we didn't think about this term. But the crazy thing is, this term is the same for every assignment of ability little a. Like when ability equals 0.01, these terms change a lot, but this term stays the same. When ability is 0.02, these terms change a lot, but this one stays the same. When ability is 0.03, you guys get where I'm going. These ones change a lot, but how about this one? Stays the same. You can see why people think about this as the normalization constant. Like, it's like everything is multiplied by some unknown number. If I knew that number, then I would know this term, but I'd also be able to calculate my updated belief. But we're going to leverage the fact that we know that all of these things should integrate to 1. The area under the curve should be 1. So if you sum up this value plus this value plus this value plus this value, it should give you 1. There's a few ways you can do this, but I chose to write a normalized function. Basically, I loop over the whole dictionary and I calculate the total. And that total will be something different than 1. But I know if I divide every belief by this total, then it turns out that normalizes your whole histogram, so the whole thing must integrate to 1. You can think about how you would like to do this. There's lots of correct ways to do it. But at the end of the day, you just need to write a function so that you take all these terms, you take all of these terms in this dictionary, and you scale them by some number, some magical number, so that if you add up all the terms, it gives you 1. And I called mine normalize. And now we have it. And you can take one belief. You can add in another belief. So this is, they got a pretty large number wrong, but then they got a bigger letter right. And then you can think about those two letters in a row. And like now we think that actually they don't see that well. Our most likely belief, if you asked me for one number, would be 0.3. But do you think Chris likes to be asked for one number? No, Chris doesn't like to represent as one number. Chris likes to give you the whole probability distribution. And there's, and one of the nice things about that is that whole probability distribution makes it easier for me to update. Let's say they get, what if they got a really tiny letter and they got it right. That's so weird. Like they took a large letter and they got it wrong. They took a larger letter and they got it right, and then they looked at a pretty tiny letter and got it right. Whoa, can it handle that? Absolutely. After this is like, okay, I have this pretty wide distribution, but now I'm starting to think that you can actually see pretty well again. And you can put in any combination of beliefs and you can update your belief. What a good way to estimate somebody's ability to see. Yes?
Do we expect this to converge in the probability distribution to eventually be really spiked?
So if you run this with real humans, after you've seen about 20 questions, your probability distribution looks like this. And you're like, I'm pretty sure. Except if, I don't know, your person is like super drunk and they're like not paying attention, like sometimes they're guessing, sometimes they're slipping. And after 20 questions, if they've been all over the place, you may end up with some more variance. And that will depend a lot on the person. But most people, pretty low variance after 20 questions. This is not that important, but there's one thing I haven't told you. Like, I've told you everything about how we update our belief about people's ability to see. What I haven't told you about is how do you choose the next letter? I'm going to tell you the answer, and in about 2 weeks, I'll explain the deeper theory to why this is interesting. If you take any current belief in ability to see, there's another reason why I like ability to see represented as a belief. Let's say that's my belief in ability to see. It's not one number, it's a whole probability distribution. If I want to choose the next font size, you know what I do? I do this thing called optimistic sampling. I take one sample from ability to see. I pull a sample from this distribution, and then I ask, what's the perfect font size for that sample? It balances out exploration of whether or not the person can see and taking advantage of what I really believe they can see. And it turns out to be a really nice optimistic algorithm for coming up with the next font size. And that turns out that other part of the problem is really important too, but it has a nice simple solution. That nice simple solution, though, requires you not to express your belief as a number, but express your belief as a whole probability distribution, which is what everyone in the world should be doing. We should all be talking about our beliefs. If somebody says like, oh, when do you think you're going to get home? I'm like, okay, wife, here's my whole chart of all the times I can get home and my belief distribution. Like that's how I'd like to express everything if I could, but that's not very good with language. Okay. I actually want to let us go a little bit early, but how cool is that? You guys have worked so hard to like build fundamentals and practice your Bayes theorem and think about your Bayes theorem with random variables, and now random variables can take on lots of values, but it leads to this ability to write programs that a lot of people seem to not be able to write, which is such a cool thing. Have a fantastic day. Come back on Wednesday. We'll continue this great conversation. Thank you guys so much for working so hard.